Okay, since today we have received one international student who just coming in and register in this course, so maybe from today onwards, I will be delivering my course in English, and maybe sometimes selang-seli lah. I think the international student cannot capture the word selang-seli. Selang-seli means interchangeably with English or some Malay. All right. So, but hopefully, most of the time I'll be talking in English. Okay. So, this is we are still in the third week, right? Third week of fourth. We are still in the third week of the lecture. I think fourth week already, right? Not so sure. How many weeks already? Next week will be fourth week, right? Which is the last week for you to add and drop course. Okay, so we are in the third week, and actually we have already finished our wait, let me share again my let me share again the barcode QR code so that you can record your attendance. So please record your attendance. Okay, so far we have already finished this topic, which is topic 1, introduction to machinery principles. And actually I have gone through all the tutorials. The tutorial video has been recorded, but still I am still uploading the tutorial videos together with the notes I will share with you guys later. Actually, in this topic we have 1.1 tutorial 1. Where is it? Okay, tutorial 1.1, and then this tutorial video has been uploaded so that you can access to that video, and also the tutorial notes also I have shared with you in the WhatsApp group. Similarly to the tutorial 1.2, I also share it and upload the video, so you can go through the video. If you don't understand or have question, just personally text me, or you can just ask in the group. Okay, 1.3 also finished, so I will not be repeating all of this tutorial because I've already recorded. I took some time to record the video so that hopefully you can follow the video even you are not in the online class. So I mean asynchronously you can follow the videos and study about the tutorial at home. Okay, 1.3, 1.4 also has been discussed. No, actually 1.4 I've asked you to submit exercise, and I've given some hints for you guys to answer 1.4 tutorial. And later, once you finished submitting, I will check your assignment or exercise that you have submitted, and then I will share also the video discussing about this tutorial, which is tutorial 1.4. This is a bit high level of assessment, or high level of PLO, right? Rubric, which is the higher level will be cognitive level 3 or 4 for this one. Similarly, for tutorial 1.5, I've already instructed all of you to submit it as exercise. So I've given the hint as well. And for this tutorial also, this one will be higher than the previous one, which is cognitive level 5. Cognitive level 5. So about this tutorial, actually I have given another hint for you to find how to find the mean path of this core, yeah, because I didn't show it during my last session. So I have shared with you on how to calculate the mean path of this core, so that you can use that calculation of the mean path to calculate the reluctances of each leg of this core, right? So about this tutorial also, I will check it, and then I will prepare the video and guide you on how to answer it, so that you can refer to the video, and the lecture notes also will be shared with all of you guys. Then 1.4, 1.5, also 1.6 tutorial. So for tutorial 1.6 also has been uploaded video in the channel, in the YouTube, so that you can refer. So basically this one also could be the cognitive level 3. Then we move on to Faraday's law, and also we have finished discussing about induced force on a wire. And then there is a tutorial, another tutorial, which is tutorial 1.7. But for this one, I've just finished recording the video yesterday. Then maybe within this week I will upload. I'll make sure that all of those videos that I've recorded will be uploaded in the YouTube within this week, inshallah. So, and again, of course, my lecture notes also will be shared with all of you. So 1.7, 1.8 also is not available yet in the YouTube, but I have already finished recording. So this question is quite easy, just straightforward. And then tutorial 1.9, also the video has finished record, but still uploading. Now for today's tutorial, I'm going to discuss on the tutorial 1.10 for the linear DC machine. So actually we have already discussed about linear DC machine in the formal lecture in the last week. I think this week lecture we have already finished this. I think since last week we have already started linear DC machine and finished discussing about it, but we haven't discussed on the tutorial yet. So today we will be going to discuss this tutorial 1.10 of linear DC machine.
Doctor, sorry.
Yeah?
The machine means it means motor?
Machine means motor or generator.
Can be either this or this.
Yes, sometimes it can be generator, sometimes it can be motor. It depends. But yeah, the general term is machine.
Yeah. No.
Yes, when I talk about machine means that it might be motor or generator, right? So for those who have any question, just unmute your mic, and then just can answer, interrupt me. You can interrupt me and just ask your question. All right. So so you have finished recording your attendance, right? So I will close this because I'm going to move on to my canvas. So this is the tutorial 1.10. I have already recorded, and I have the notes here. So as you can see from this tutorial note, so as you can see from this tutorial note, I've already drawn the circuit that represents the DC machine. So this circuit is actually the same as this one, appears in your lecture notes. So basically for this linear DC machine, we are going to discuss on how to to define whether this machine is working as a generator or motor. So it depends. It depends on how we apply the force on the bar. We have the bar. This is the conductor bar actually. So we have this conductor bar, and we have the supply here, which is the battery supply. If we switch on the switch here, the current will be flowing through this resistance, through this resistor, and then it will be keep flowing in this bar and go back to the battery. So at the instant of we switch on the battery, we switch on this switch, at the instant of this switch is switched on, okay, there is large current will be drawn by the machine to large current will be drawn by the machine, which cause the bar, which cause this conducting bar to move to the right direction. So as you can see, Ff is the force applied to this bar because of the switching. Because of that switching, a large current will be drawn by the machine, so that this bar will be moving toward the right direction at speed of v. So that is speed. At the speed of v, this bar will be moving to the right. Why to the right? Because we can use the right hand rule. The right hand rule we can use the right hand rule for the current carrying conductor in the magnetic field, right? So we know that the force will be acting on that direction, to the right direction. So the question is, what is the machine maximum starting current? So we know that at the instant of this switch is on, a large current will be drawn, which is passing through this resistor and then to this bar. So at that time there is no E in. The voltage is not induced yet in this bar because it just started. So we have to know that situation. Once it is started, there is no induced voltage yet applied or appears across the bar. So meaning that if you use this equation, induced voltage equals to VBL. V is the velocity, B is the magnetic field intensity, and L is the length of this bar. If we apply this equation, that we know that induced voltage is 0. Okay, so that is at the instant of the switching, meaning that V is also 0. Okay, V is also 0. So induced voltage is 0. So using Kirchoff Voltage Law, it is simplified by KVL. So using Kirchoff Voltage Law, we can use this equation. VB equals to E in plus IR. Okay, the voltage appears across the battery equals to the induced voltage because of the bar carrying current moving in the magnetic field, and this is the voltage across the resistor. But at that instant, we know that induced voltage is 0. So induced voltage is 0. Then we can further rearrange this equation to find current, which is the instantaneous current at the switching, which is I equals to VB divided by R here. So we know that the battery voltage is 120 divided by R, which is 0.3. and we get 400 for the starting current. Okay, so that is at the instant of the switching, meaning that if you can see this graph, just now I am talking about this area at the instant of the switching. So move to second question. What is the steady state velocity at no load? So what is the steady state velocity at no load? So once we start the motor, the bar will be moving. The bar will be moving to the right direction at initial speed, and then the speed will be increased because of the force, because of the induced force. The speed will be increased up to some time. It will be constant, which is, we call it as the steady state speed, which is VSS. Yeah. So once the bar is moving, meaning that we can apply VBL, right? Which is the voltage starts to induce across the bar. So the voltage starts to induce across the bar because at this instant we have V. So voltage will start to induce. So we have V here until sometime it reach the VSS. Okay. So at VSS ni, we know that it achieves a state of equilibrium, which is balance, meaning that the induced force is now, induced force vector in that direction, to the right direction, is now the same as the induced voltage. That sort of thing. Okay. All right. So now we want to find the steady state. Now we want to find the steady state speed. So we know that at steady state speed, at steady state speed, it achieves the state of equilibrium, which is balance, which is balance, meaning that VB now is equals to induced voltage. So VB now equals to induced voltage, meaning that we have VB here. So on our right hand side, voltage will be induced like that. This is VB. It is balanced now. So this is the state of, we can say that this is the state of V achieve VSS. So in this case, we can just use this equation. VB equals to induced voltage equals to VSS BL. Okay. So further rearrange this equation, we can get the VSS by using VB divided by BL. So finally, in this case, we get steady state velocity, which is 120 meter per second. All right. And then, so once we get the VSS, meaning that this machine is working as a machine which is no load applied to this machine, and it is working as a motor. So at this instant, this machine is working as a motor. Now, what happened is, back to the question number 3, what happened is, we are trying to apply the force. We apply the force pointing to the right, okay, pointing to the right of the bar. So what will be the steady state speed be? Okay, So we know that we start the motor, we start the machine lah. I am going to use the term machine now. Still machine. We start the machine, and then it achieves its steady state speed. The shaft is rotating at steady state speed, and then what happened is we apply the force to the direction of the applied force. Okay. We apply the force to the direction of induced force, actually, not applied force. Let me redraw this to make it clear. Actually, the situation is like this. The situation is like this. We have the bar. I think you can, I hope you can see uh, what I am trying to draw now. So we have the bar. From previous question, it is moving at the speed of VSS, and also it has force applied, force induced in it, because the current is flowing in the bar, and then it achieves the steady state speed, right? It achieves the steady state speed, which is, if I can write another vector here, which is, once it achieves the steady state speed, meaning that now the induced force is equals to induced voltage. Okay, we already know that. So now for the question number 3, what happened is we apply force, we apply another force toward right direction. We call it as F applied. Okay, we apply force toward right direction. So we want to find the new steady state speed. Okay, we want to find the new steady state speed. So this bar will achieve new steady state speed once we apply the F applied to applied force. It achieve new steady state speed when it achieve the balance, achieve balance state VSS prime. I name it as VSS prime, not VSS prime. It's VSS final. VSS final. So it will achieve VSS final after FF equals to F in. Can you see that? So after applied force equals to induced force, it achieves another steady state speed. It achieves another steady state speed. Meaning that we can use the applied force of 30 Newton firstly to find the current. Okay, we can use applied force of 30 Newton to find the current using ILB. So FILB, F applied goes to ILB. F applied equals to IB. Further rearrange the equation. Then finally we get a current of 30 amperes. Okay. So that is the current during VSS. Sorry? Can you mute? Avinash, can you mute your mic? Are you okay? Avinash, is that all right with you?
Doctor, sorry, doctor. My line. Sorry, doctor.
Okay, no problem. Okay, so back to this question. Okay, so firstly, we can use the 30 Newton, that 30 Newton, okay, to find the current first. At this instant, at this state, we still not calculating the VSS final. Okay, so we get the current, and then which is similar to the magnitude of the force, which is 30 ampere. We get the current 30 ampere, and this current is actually flowing back to the battery. Okay, meaning that if we have the bar, if you had this bar, it is already have the force induced to the right direction, and then we apply another force. What happened is actually we are turning this machine into generator. Okay, into generator. So this machine becomes generator. At this instant, actually the induced voltage is larger than battery voltage, which is generator action lah. So so the current that we just calculated, 30 ampere current, actually moving from uh, bar side to the battery. If I can further uh, draw this, it will look like this. So I have my resistor here. If I simplify this machine, now we have induced voltage at the right and VB at the left. So current is now flowing from bar to the battery, which is it is trying to charge the battery. So it is trying to charge the battery. So we know that the current is actually moving counterclockwise. So this is the generator action. So similarly, I have already drawn here the same thing. So induced voltage is now larger than VB. Okay. So current will be flowing counterclockwise, which is battery is now being charged. So now we know that induced voltage is larger than VB. The same thing we apply Kirchoff Voltage Law, KVL. So induced voltage equals to VB plus IR lah. Because induced voltage is larger than VB, so induced voltage equals to VB plus IR. So it is plus IR because induced voltage is larger than VB. In the case of machine working as a motor, VB will be larger than induced voltage. So we in that case, we can say that VB equals to E in plus IR lah. Okay. So now we are talking about generator. So we will be using this equation to further calculate the induced voltage. So just now we got the current. So we have the induced voltage 129 volt. Now we can say that 30 amperes current, this is 129 volt, this is 120 volt. 30 amperes of current is flowing into the battery. So at this state, the machine or the generator has already achieved its steady state speed, which is new steady state speed. We call it as VSS final. Then we can use the same equation, which is VSS final equals to E in divided by PL. Then we substitute all the values that we got just now. And finally, we get 129 of the steady state speed final. Okay. So earlier we got at the no load, earlier the steady state speed was 120. Now it increased to 129. So from 120 increased to 129. So question number 4, how much power will be the bar be producing or consuming? So in the question, it is either producing or consuming at the bar side. Now we want to find power at the bar side. All right. So we use P bar. No, we want to find P bar. So we can conclude that the bar is producing power. Why? Because the bar is now working as a generator, right? So when the bar is working as a generator, we can simply use this equation, because at the generator side we have induced voltage times the current that is flowing to the battery. So we get the P bar, which is 129 times 30. Okay. So at P bar or bar side power, we have 3870. Okay? 3870, which is the power at the bar. Okay. So as you can see, my illustration here. Okay. P is 3870. The power from the bar. So that is the answer for question number 4, which is the bar is producing power. Okay, not consuming, but producing power. If we look at the battery side, battery is consuming power. And if we look at the bar side, meaning that the bar is producing power. So it is working as a generator. And similar to question number 5, we can explain it by this calculation. We can explain it that the machine is acting as a generator. Okay. All right. So I have also shown here how to calculate the battery side power, which is using P bat here. So voltage of the battery times current. So we get 3600 watt. Okay, 3600 watt. This is at the battery side. Okay. So at the battery side, we have 3600. At the bar side, we have 3870. If the question asks us to find the power loss, if the question asks us to find the power loss, we can use this equation. P loss is I square R. Okay. So I square is 30 square, which is 30 amps. All right. Times the resistor of 0.3. So we get about 270 watt of power dissipated across this resistor. So we have the power loss, power from the bar, and power from the battery. Then, of course, we can also calculate its efficiency. The generator efficiency by using the P out by P in times 100, right? Okay. So P out is from bar side, which is P bar, by P in is the battery, P bar. times 100. So P bar, sorry. If the question asks us to find the efficiency, we can use this equation, which is P out divided by P in times 100. So P out is P bar. Okay, P out is P bar because it is working as a generator. So P out is P bar. P in is P bar times 100. So P bar 3600 divided by 387 T 70. So how much is the efficiency? How much is the efficiency of this case?
90.0.
Liza, saya tak dengar. Sekali lagi. Can you repeat? What?
93.02.
93.02, right? Okay. So efficiency in percent is 93, about 93% lah, which is 7% power loss. This 7% is actually about 270 watt. All right. Okay. So that is up to number 5. Now, there is another situation. There is another condition where suppose that 30 Newton force pointing to the left were applied to the bar. Now, we apply the force to the left hand side of the bar. Okay? Mana we are trying to oppose. We are trying to oppose the bar. Meaning that, for example, if we start the machine like we start the hand drill, for example, when we start the hand drill, it will be starting and then rotating at steady state speed, which is no load speed. We call it as no load speed. Once we are trying to drill the hole, meaning that we apply force opposite, opposite to the initial rotation, opposite to the force, initial force acting on that shaft, right? So we call it as we apply F load, the force, the load force. Okay, so 30 Newton is actually the load force. As you can see in my sketch here, so we apply 30 Newton of force to the left hand side, and the bar was moving at the steady state speed. So meaning that we apply F load lah. We apply F load to the left hand side. So what happened is the bar starts to reduce its speed. The speed is reducing up to another steady state speed. Okay, as has been written here, suppose F load is applied as in the figure. F load 30 Newton is applied as in the figure. What will be the new steady speed? New steady state speed. Okay, initially it was 120 meter per second. That one is the initial steady state speed. Now, once we apply the force, which is F load 30 Newton, what happened to the new steady state speed? So we can imagine that the new steady state speed must be reducing. We know that it is reducing. It is reduced, but how much? Okay. So similarly for this illustration, as you can see, we have VSS as initial steady state speed. Then we apply F load. So when we apply F load, after some time, it achieves VSS prime. Yeah, it achieves VSS prime. At that instant, it is actually induced force is equals to load force. So induced force vector is now equals to load force vector. Okay. So similarly, we can conclude that the new steady state speed must be smaller than VSS, which is the initial steady state speed. So back to this concept, back to this situation, we can derive the equation like this, which is now F load is equals to F int, which is ILB, meaning that we have new current. We have new current flowing inside the machine, which is new current will be found using I equals to F in divided by LB. Okay, ding dong ding dong. I equals to 30 amps lah. So we get the new current flowing, which is 30 amperes. So, but this current is now flowing down. This current is now flowing down through the bar, which is this machine is now working as a motor. Okay, so we can always say that if the machine is working as a motor, meaning that VB is always larger than the induced voltage. So VB side is always larger. VB side is always larger than the induced voltage. So if I can draw the current, it is now moving clockwise direction, which is I is 30 amps. 30 I is 30 amps. I is 30 amp. Okay. So once we establish this, VB is larger than induced voltage. Similarly, for the KVL, Kirchoff Voltage Law, we can use this equation, VB equals to E in plus IR, because VB is larger than induced voltage, right? So we can rearrange this equation to get new, this is new induced voltage, which is substitute the values of VB and current and also resistor. We get the new induced voltage of 111 volt. Okay, and then once we get the induced voltage, we can use that induced voltage to calculate the VSS prime, which is new steady state speed. So E in divided by BL. Similarly, we get new steady state speed, which is much more slower lah, much more which is decreased speed, decreased speed to the earlier speed of 120 meter per second. Now the speed becomes 111 meter per second. So that is explanation about number 6, question number 6. So when we apply force of 30 Newton, what happened is what happened was the motor will work as the machine will work as a motor, and then the initial steady state speed becomes decreased to the new steady state speed because of the load that we apply. So this machine is now working as a motor. So to answer this question number 7, so this machine is now working as a motor. So the concept was easy. If we see this figure, right, once this machine is achieved to the no load speed, okay, so it depends on us. How do we apply the force? If we apply the force to the same direction where the machine is rotating, machine is where this bar is moving, okay, so meaning that we are converting this machine into the generator. Okay, so similarly, if we apply force opposite to the direction of this bar moving, which is to the right direction, for example, at that time, we are turning this machine into the motor. Okay. So I think that's all for the explanation of tutorial 1.10. I don't think I have more time to explain on the tutorial 1.11, but actually I have already recorded I have not yet recorded the video, but I have already written my notes. I have the tutorial note here, which I will be sharing with you later. And also at the same time, I will prepare the video discussing on this tutorial, which is tutorial 1.11. Then I will upload it later. So up to this tutorial 1.11 ini, we have already finished topic 1. All right, we have already finished topic 1. It is going to rain now. Okay, so we have already finished topic 1 with 11 tutorial. All 11 tutorial we have, and I will make sure that all of those tutorial will be also prepared video on how to answer all of those tutorial, and then I will upload it in my YouTube channel, and I will share my tutorial note as well. So you guys punya task is just to sit down, watch the video, and try to understand on how to answer the tutorial question. And I would like also to remind all of you to submit your exercise, as I just noticed in the e-pembelajaran, e-learn, that there is nobody submit. There is no one submitted. All right. Okay. 8 already. 8 students already submitted. So we have 4 students left.
Doctor, is it possible to extend this submission? Because I cannot. I need, or I will start from the next submission.
Actually, this exercise is not applies for the assessment. This exercise didn't apply for assessment punya marks. Assessment mark is not applied to this exercise. But
okay.
Actually, if you like to follow this, I will upload later the discussion about tutorial 1.4 and 1.5 so that you can follow. This is just for the exercise. If you want to do the exercise, you can have a look at this. I think you can access this, right?
Yeah, I can.
You can download this and have a look at the tips that I've given in this tutorial, and then try to answer. And then after that, I will share the answer, including the methods, including the way how to answer that. Okay. Okay. So I think I would like to finish up to this time for this meeting, so that you can follow another class. All right. So if you have any question, just drop me WhatsApp personally or in group. Okay. So since we already finished this topic 1, maybe I will upload the first assessment, which is quiz 1, by next week. Okay. By next week, I will upload quiz 1, so that you can answer it online. This is online quiz based on topic 1. Okay, clear? Okay, so anyone have any question?
Doctor, for the current direction, is in electric is considered from negative to positive or positive to negative?
Which current direction are you talking about?
In circuits, if we example, we have a circuit, we can see a battery, And
Yes, if it is working as a motor, if this
yeah,
machine is working as a motor, meaning that current direction is now from battery to the bar.
yeah, but it's moving inside the wires from negative to positive or positive to negative. It means like
Inside the wire,
yeah,
let's say if we have this figure, if
yeah,
this motor is working as a this machine working as a machine, this machine is working as a motor, meaning that the current direction is to the clockwise direction.
okay,
So meaning that the battery is supplying the bar with the current.
yeah.
Okay. So any more question? No, So we have another 4 minutes, but I think I would like to stop up to here. Okay. So just keep on checking your eLearn and also YouTube channel so that you can get latest update from there. Okay. So I think that's all for today. Thank you so much. Then
You're
until
welcome.
we'll see you again next week.
Okay, Doctor.
Sama.
Doktor, saya belum scan QR code lagi.
Siapa? Sekejap. Nampak? Dapat? Siapa? Civagesh ke? Avinash?
Okey, doktor, dah boleh. Thank you.
Okay, sama.